Yes, class. So in the last class, we had stopped at this point, moving coil galvanometer. We didn't do the conversion of galvanometer into either ammeter or voltmeter, but we had started with the introductory part of moving coil galvanometer. We had seen it's a device. Galvanometer is what? Galvanometer is basically used to detect current. Principle includes principle of moving coil galvanometer includes that a current carrying coil that is placed in magnetic field experiences current depending torque. That torque tends to deflect it, and because of that deflection we are able to observe it on the scale or with the help of a pointer, and this is the only part that we are able to observe. So theta, that was the deflection, came out to be NAIB divided by K, where N was number of turns, A was area, I was the current flowing, B is the magnetic field, and K is the torsion constant. Torsion constant will be provided to you. And then two types of sensitivities we had seen. One was current sensitivity, which was deflection divided by current, and voltage sensitivity, voltage divided by deflection divided by voltage. Two small topics were left to be covered on that day. One was conversion of a galvanometer into an ammeter. So if you just have a simple galvanometer with you, let's say this is a simple galvanometer that you have. Now I want to convert this galvanometer into an ammeter. Just a second. If I want to convert this galvanometer into an ammeter, the best possible way is to connect a resistor in parallel with this galvanometer. Galvanometer has its resistance G. G is what? Resistance of galvanometer. This parallel resistor, this parallel resistor connected in this way, this is known as shunt. So to measure large currents with it, a small resistance is connected in parallel with the galvanometer coil, and we call this resistance which is connected in parallel as what? This is known as shunt. So shunt has what? It has a value of low resistance. Low resistance is there, and this is connected in parallel. These are the 2 points that you have to remember for any values of shunt. Fine. And I is what? I is the total current that is coming from the circuit. And as I've mentioned already over here, IG is what? IG is the current that is crossing the or passing through the galvanometer. So IG is the current across this galvanometer. G is the resistance of this galvanometer. S is a shunt resistance which is connected in parallel with it. Fine. Now, obviously, from the total current I, if IG has been abstracted, then how much will be left? I minus IG will flow through this. I minus IG will be left through this. Right, class? So I minus IG is what? Current through the shunt. IG is what? Current across the galvanometer. G is the resistance of galvanometer, and S is the shunt resistance. Fine. Now see, class. If these are connected in parallel, then name the quantity that remains the same. Which quantity remains same in case of parallel combination? One quantity that remains the same. Yes, right. Z, do you have to leave right now? Okay, that's fine. So yes, Z is right, it's voltage. Potential difference remains the same. So whatever is the potential difference across the galvanometer, I'll write it down. Potential difference across galvanometer is equal to potential difference across the shunt. So this is what? Potential difference across galvanometer is equal to potential difference across shunt. Why? Because these are connected in parallel, and we have already studied that in case of parallel combination, the quantity that remains the same is the potential. So here potential across the resistor, across the shunt as well as the galvanometer will be the same. So current is here what? Current across the galvanometer. Current is IG. Resistance is G. So potential will be what? Here Ohm's law is V is equal to IR. So potential across the galvanometer will be IG into G. Current into resistance. This is total is giving you what? Voltage. Now current here is I minus Ig. Resistance here is S is the shunt's resistance. So this becomes I minus Ig into shunt's resistance value. Fine class. Now from here, if you want to find out the value of the shunt will be equal to what? Ig into capital G divided by I minus Ig. This becomes the formula of shunt. Now you can easily calculate the current. Your galvanometer has been converted into ammeter. So an ammeter is what? It's a shunted or low resistance galvanometer. Now, shunt is what? A shunt is a low resistance which is connected in parallel. This I was telling you. Shunt is what? Shunt is a low resistance connected in parallel. These two things you have to remember because this is the only point that makes the conversion of galvanometer into voltmeter different from conversion of galvanometer into ammeter. So shunt is what? It's a shunt is what? A low resistance which is connected in parallel. Remember, do not connect it in series. Otherwise, whenever you will do it practically as well, you won't get your results. So now we'll be able to measure the current also, everything that we were using earlier for our meter that are successful right now. So quickly copy this and we'll see what is the conversion for a voltmeter. Done. Shunt is not an ammeter. This whole device now that has been constructed, this complete, earlier it was just this galvanometer. Now this complete setup, we call it as an ammeter. Because now you will be able to measure the current. And what's the function of an ammeter? To measure the current. Your purpose of using or converting a galvanometer into ammeter is to just find the values of current. Using these formulas, you already know the value of shunt resistance. You already know what's the resistance of galvanometer. And total current, you also know that we supply. So you can easily calculate the current that is flowing across everywhere. So that is the function of an ammeter. That's why we just use this. Now conversion of galvanometer into voltmeter. So again, if you just have a plain simple galvanometer with you, a galvanometer you have. So here, instead of connecting anything in parallel, I'll connect a small resistor in series with it. But now this resistor has high value of resistance. So resistance of galvanometer is still G. Let's say the resistance of this resistor is capital R. And again, current that is flowing through this is Ig. So G is what? G is the resistance of galvanometer. Ig is the current through the galvanometer. R is a high series resistance. Shunt was a low parallel resistance. Here R is a high series resistance. This we do not call it as shunt. Shunt was specifically for parallel low series one. Low parallel one. For this we just use the term resistor. And V is the voltage applied across it. So G is the resistance of galvanometer, G is the, and R is the resistance of this resistor which is connected in series. So all of you quickly reply me in the chat box what should be the value of R equivalent. Series, parallel combination, everything we have done. What will be R equivalent over here? Yes, class. Resistance of galvanometer is capital G. The resistance of this resistor is capital R. You know these are connected in series. So what will be the equivalent resistance of this? No, Zed, no. Others? Yes, Zed. Now it's fine. Nobody. Just a second. Okay. So it's fine. So initially also it was right. Not subtraction sign, Sahal. See, in case of resistors, we never subtracted. We always added. Earlier also when we were doing equivalent parallel combination, there also we had seen. Though the voltages or EMF got subtracted, but the resistance always got added. We always added the internal resistance. In case of series, formula is what? R1 plus R2. So this is R plus G. This is the net resistance. Current is what? Current is Ig. So using Ohm's law, potential will be product of current and resistance. So potential will be equal to current is Ig, resistance is R plus G. Fine, class? Now, what will be the value of R plus G? From here we can say, from here if you try to find out the value of R plus G, R plus G from here, this will be equal to IG, no, V divided by IG. And what's the value of this unknown resistor? This will be V by IG minus G. This becomes the formula. From here, using this formula, you can modify it into any manner you want. You can find out the value of G, you can find out the value of R, any quantity that is unknown. But remember, resistance of voltmeter will be Rg, that is the G resistance of galvanometer plus the resistor. Before you note it down, just one more thing. See, always remember this fact that if your voltmeter is ideal, if you have an ideal voltmeter, so what happens for an ideal voltmeter, your resistance value is infinite. Your resistance value is infinite. For an ideal ammeter, your resistance is zero. Because obviously, see, I is equal to V divided by R. If R is zero, then I will be equal to what? V by 0, and 1 by 0 is infinity. So current will be infinity. It means we will get such a huge amount of current. Ideally, definitely it's not possible. You cannot get a resistor whose exact value of resistance that it is offering is 0. You cannot get value infinite for a wire that is present. And that's the opposite for a voltmeter. Current is almost equal to 0, so resistance becomes infinite. So these are the points that you should just write for your understanding. But these two are important. In your theory questions, these can be asked. What's the value of resistance for ideal ammeter and voltmeter? Fine, class. Copy this down as well. Then we'll do a numerical based on this. See class, this question says what it says: an ammeter of resistance 0.8 ohms. So this is the resistance of the ammeter. So it means what here? This galvanometer has been converted. So this shows that this is value of G, capital G that you have. So capital G is 0.8 ohms. Okay, capital G is 0.8 ohms. So from here, this can measure currents up to 1 ampere. And what will be the current across the galvanometer? Current across the galvanometer is Ig. This is given as 1 ampere. This is what is meant by the first line. An ammeter of resistance 0.8 ohm. Resistance of ammeter is what? Definitely ammeter has been converted by the galvanometer. And second, measure currents up to 1 ampere. So this is the current of the ammeter. What must be the shunt resistance to enable the ammeter to measure current up to 5 ampere? So this is the current. In the first part, this is the current that is given. That your current is 5 ampere, find out the value of shunt. So this is not a tough question. Shunt will be equal to Ig into G divided by I minus Ig. You will get these kinds of question only in your exam. So value of shunt will be what? See, S will be equal to Ig 1 into 0.8 divided by 5 minus 1, right? Yes. This is 0.8 divided by 4, that becomes 0.2 ohms. Second part says what is the combined resistance of ammeter and shunt. So ammeter and shunt, how are they connected? Series or parallel? Yes, class. Respond. Series or parallel for shunt and ammeter?
Parallel.
Parallel. Good for him. They are connected in parallel. So if resistance of the, let me just write it in terms of geometry. If the resistance of galvanometer is given as 0.8 ohms and the resistance of the shunt is given as 0.2 ohms, and both these G and S are connected in parallel. So if they are connected in parallel, I cannot directly add to get the combined resistance. So here you have to apply all your concepts of current, electricity. We had studied all these things so much in detail. Till this lesson, till chapter 4, we have studied everything so much in detail. All the topics with their separate headings, because this was the core portion. And I think most probably in your half yearly exams till here or the next chapter it should come. So 1 by R equivalent will be what? 1 by G plus 1 by S, which is equal to 1 by 0.8 plus 1 by 0.2. So R equivalent will be what? G into S, 0.8 into 0.2 divided by 0.8 plus 0.2. This is 16, 0.16 divided. This will be directly 25 by 4 also I can write. This is 10. So this becomes 1. So this is 0.16 ohms. So this is the R equivalent. So you cannot forget your previous concepts. Let us just complete the 1 or 2 chapters, then we'll have very revision classes, very long revision classes for all these topics. Just note it down. Any doubts from this lesson? So this was the last topic. So your moving charges and magnetism has been ended. Just let me know when you all have your half yearlies. Others, Zaid, I know. Zaid, I remember. Zaid has told other students when you, I think, just wait for your school to get reopened. When your school will get reopened, just text me either on the WhatsApp group or personally on WhatsApp or in the class. Tell me whenever is your half yearly in whatever syllabus you're having, because whatever will be the average syllabus for all of you and approximate. According to that, we'll be having the revision for your half yearlies, because electric charges and field is there, potential, capacitance, current, electricity, and then this lesson. 4 major chapters are there. Chapter 5th, we'll start today. The chapter 5th, you can easily observe how small and easy is chapter 5th. Everybody has done? All right. So now we will start with your next chapter, that is your magnetism and matter. It's a very short lesson. See, Earth magnetism, we'll do it at the end after completion of alternating current. That time we'll do, or we'll do it after. First, let us just complete the major portion of it. Bar magnet is important. Bar magnet is very important from your understanding. Now, your syllabus, major basic portions of electrostatics, electrodynamics, and magnetostatics. These have been covered already till fourth chapter. That's why I was constantly emphasizing from the first day that please, till these 4 lessons, we'll go slow. Try to complete all of these. Now, these are very short lessons. EMI, AC, magnetism and matter, all these 3 EM waves. These are now everything that is left from your first one. These are very short lessons and they'll be completed quickly. So, and now the basic concepts we have studied, now we'll be just relating things. So introduction is what? We deal with the natural magnets or permanent magnets. Your natural magnets, these include your bar magnets. Natural magnets, these are your bar magnets. Horseshoe magnet, which are constructed. So many magnets. And permanent magnets, permanent magnet means your earth magnetism. One of the examples can be dealt. Earth magnetism, we'll be having a separate class for it. Now, bar magnet is what? Bar magnet is an artificial magnet. It's an artificially constructed magnet, but one of the properties that is included in bar magnet is that the artificial, though it is artificial, but it is a permanent magnet. Once made, then it retains its properties. It's a permanent magnet. Now, there are certain properties of these bar magnets. First property is the attractive property. Attractive property means North Pole will attract South Pole. And South Pole or North Pole will repel each other. These will repel each other because these are unlike poles. These are like poles, and unlike poles will attract each other. So this is the attractive property that is executed by the bar magnets. Second property is the directive property. Initially, we'll be talking about the terms first. Then we'll go into the main chapter. Then second property says directive property. Directive property means if from a freely suspended bar magnet is there. Let's say this is the freely suspended magnet that is held. This is held, let's say north-south. So ultimately what will happen? You have left this freely suspended magnet with the help of a thread. You have tied it over a rigid end. Now, once you will leave this, this will align itself automatically in this north to south direction. Like this, it will align itself automatically. That is what I have written. Freely suspended magnet always align itself in north-south direction. This is the second property, that is the directive property. Fine, class? So first property was what? Attractive property. Second property, directive property. Third property means if you have a bar magnet, and at the two ends, you have a north pole, you have a south pole. Now, somehow, if I break this part and I distribute it to 2 students, let's say one north part, I have given it to Darshan. So Darshan has this part, north part. And second part, this part I have given it to Rifat. So Rifat has south polarity part and Darshan has north polarity part. But actually they are not having the north or south polarity. This part, this will develop south polarity automatically and this part will develop north polarity automatically. It can never happen that only the edges or a single pole exists. This is the reason, because magnetic monopoles do not exist. Magnetic monopoles do not exist. Magnetic monopoles means what? Single pole. Just a second. Single monopole means what? A single polarity is there, either north or south. The way in electric charges, you had bipoles, two poles you had, dipoles you had no. One was what? Plus charge and minus charge were there together. But even monopoles did exist. If you had an electron with you in any sphere, then using that electron, you can easily calculate the charge on it, the mass of it, all the properties of it. So single charge is there. For a proton, let's say a positive charge, it will exist on it. But if you have dipoles with you, that will also exist. In case of magnets, monopoles do not exist. In case of magnets, monopoles do not exist. Magnetic monopoles never exist. If even if you have at one edge you have north polarity, at other edge you have south polarity, this breakage will result in the construction of it. This is the third property. Fine class. And then last property is magnetic induction. Magnetic induction means, for example, I have an iron ball. This is an iron ball. And I have a bar magnet with me. Now, if I continuously rub this iron ball on this bar magnet, continuously I'll be hovering it and rub it. Soon I'll notice that this iron ball will also become or having temporary magnetism. So magnetic induction is what? Magnets induce magnetism, where magnets induce magnetism in magnetic substance. So magnets induce magnetism in magnetic substances. For example, you can take the best example as the iron ball. So magnetic induction, four properties, terms, we have not started with the terms. These are four properties that are existed by a bar magnet. Magnetic induction, it will induce magnetism. Magnetic monopoles will never exist. Even if you take a freely suspended magnet, it will align itself in north-south direction. And then attractive property, definitely magnets attract, that we all know. Just write these terms, introductory terms, and we'll go on to the terminologies that are used in magnetics. Now, certain terms you have to remember that are related to magnets. So, one of the terms that you have to remember is magnetic polarity. So, polarity we have studied. Polarity we have already studied. This is south polarity. We know even the direction of current, and then there is north polarity. These are the two polarities. This we have studied. Two polarities, two poles exist. North pole and south. These are the terms that are essential for specifically a magnet. Now, magnetic axis is what? This is a bar magnet, north south. This central axis that divides the north and south pole in transverse plane. This axis is known as the magnetic axis. This is the definition. Magnetic axis is a line passing through north and south pole. So it's a line passing through the north and the south pole. Then one thing that you have to understand is magnetic equator. Magnetic equator is essential when we have to do the questions on equatorial plane. So north pole is there, south pole is here. Magnetic equator is perpendicular to magnetic axis. See, this was what? This line, this was magnetic axis. This perpendicular line which makes angle of 90 degree, this is known as the magnetic equator. And one last terminology before we actually start with everything is magnetic length. So magnetic length is what? If this is North Pole, this is South Pole. Magnetic length means the separation between North and South Pole. So magnetic length is what? It's the separation between North and South Pole. All right, write down these terminologies and we'll do a comparison between electrostatics and magnetostatics. So that will be a revision also from electric charges and field. We'll be have a revision of all the formulas and we'll then convert it in terms of magnetics.
Ma'am, can you scroll down?
No, the magnetic length does not separate north pole and south pole from attracting. It's just the length of a magnet. North pole is there, south pole is there. So this length of the magnet, that is known as the magnetic length. Now in comparison between electrostatics and magnetostatics, first thing in case of electrostatics, the intrinsic or basic property that you have, that's the electric charge. So plus Q or minus Q, two types of electric charges that you have with the SI unit as coulomb. Fine. And then in case, same thing in case of magnetostatics, this magnetic charge. This is actually, you do not have exactly charge that we say. We have magnetic strength. We call it as plus M and minus M, the strength of the magnet. This we call it as magnetic strength. So strength between this plus M can also be there, minus M can also be there. So this is the first basic comparison. So electrostatics, you had charge, here you have magnetic charge. Then in case of electrostatics, dipole was what? A set of positive and negative charge separated by a distance, let's say 2a. So magnitude of dipole moment was given by magnitude of one of the charges multiplied by the separation between them. Class, please pay attention to the left hand side as well, because you have studied this, but still you have to revise it. So this will be a way to revise this. And the SI unit of dipole moment is coulomb for charge and meters for this. All right, class, this is for it. Then magnetic dipole will be what? Similarly, plus M and minus M will be have a separation, 2A or A, anything you can even take L directly. Let's take L to differentiate it between magnetic and electric dipole, let's say. So magnetic dipole moment, this will be M into L. Magnitude of one of these and length. One more formula of magnetic dipole moment we had seen, that was I into A. Current into area, but that was valid for a circular coil. Generally, we have this formula for a bar magnet. Fine. So SI unit also, you can write this also, ampere meter square. Fine. This is the magnetic dipole. Two things done, charge and dipole. Then electric field. Electric field in case of axial line, if this is a positive charge, this is a negative charge. So at a certain point, let's say A point, this separation from the center. So from the center, this separation is what? This separation is R. And this separation is A, this separation is A. So 2A, definitely this is the middle, so it will be A and this will be R. So formula for this is what? Formula of electric field is 2kp divided by R cube, or let me not write k because k, both the values of constant are different now. So this is 2 times 1 over 4 pi epsilon naught 2kp by R. This is the or axial line. Now just convert this. If you have plus m, you have minus m, and at this particular point you are calculating.
E is the dipole, right?
What? P, yes, dipole moment. Dipole moment. And similarly, here you have a point A, the separation, let's say, is R, the separation is L. So you can write, just convert this. No need to even look at this or derive this or something. Just convert it to K. So 2. What is K? Constant in case of magnetics is mu naught by 4 pi. That 2K P, you do not have dipole, electric dipole moment. You have magnetic dipole moment divided by R. Like this. So this part is easy. This lesson is easy, honestly. This lesson is easier than the last lesson that we have ended. And then equatorial point, for example, plus Q, minus Q are there at this point, some point A. This is R, O. Again, this separation is 2. So for equatorial point, you have minus Kp divided by Rq, which can be written as minus P by 4 by 3 epsilon naught Rq for electric field. Now, no need to do anything for magnetics. Just convert the analogs. Similarly, this is point A, this is R, this is 2A. This lesson you will find it easier, and rest of it is theory part. So you will be able to do it. Magnetic field for equatorial point will be what? See, K minus K is what? Mu naught by 4 pi here. It was 1 over 4 pi epsilon naught here. This becomes mu naught by 4 pi. P, so this becomes magnetic dipole moment by R. So whatever you have studied, that's why it is said, focus on the first 4 chapters well. Other upcoming chapters become easier. Then torque. Torque also we had seen in case of electrostats. Yes, Fahad.
Ma'am, why minus?
Minus forgotten. Minus sign indicates that direction of dipole and electric field are opposite. So just that's why we added. Fine. Okay. And for axial, it is the same. Just revise once. Not you must have written it. So electric field's direction for an equatorial point, a point located at the equatorial axis. This is opposite to that of dipole. If dipole is from negative to positive, it will be opposite to it. That's why we write this negative sign, just to indicate the direction. Torque we have seen in case of electrostats, that is P cross E, where E is the electric field. That is can be also written as PE sine theta. Same thing in case of, this was 5th point, no? This will be dipole, electric dipole moment becomes magnetic dipole moment, electric field becomes magnetic field. This I think we have already discussed. This is MB sine theta. Fine, so remember this, you will remember this. Last thing that we'll do is work done. So see, work done for potential and not potential, for work done and potential we will see. So potential will be the work done only. Work done will be what? See, if these are your electric field lines, it is a revision. Pay attention, class. Your dipole is here, plus Q minus Q is here. Let's say 2A is the separation between. So it will change its angle. This is theta. It will change its angle. That will become some different angle, theta 2. This was theta 1, other become theta 2. So here work done, remember it was what? P dot E. P dot E, or work done was written as PE cos theta 2 minus cos theta 1. And same thing with potential energy, PE cos theta or P dot E. Just convert these analogues. In electrics, instead of electric field lines, you have magnetic field lines. In case of electric charges, you have the magnetic strength, which we call as the magnetic charge. It will also shift. There will be one angle theta 1 when it will be angle theta 2. So work done here, this will be, instead of P dot E, this will be M dot P. Work done here will also be MB cos theta 2 minus cos theta 1. And potential energy will also be MB cos theta, which will be equal to M dot. So if you remember this part well, understanding the magnetics is easier. It's just a revision. Fine class. This was a major comparison and a revision of electrostats and comparison and differential points between electrostatics and magnetostatics. So major part of this lesson is this only. This, and then few small topics are there. Then another major part includes your theory part. So this was one of the major parts. Just note it down. The second point, Z. Second or the first one? This one? Oh.
Ma'am, there are two angles in magnetic field, right?
See, two angles if they are given. See, like let's take the example of this electrostatic one. So plus Q minus Q, this is forming a dipole. Now at one angle this is kept. We'll see one more question, not today definitely, but in the next class we'll try to complete that question where you will see what's the value of torque that you're getting. And again, torque you have already studied, PE sine theta is there. So torque will try to do what? It will try to align the dipole along with the electric field. That will be the purpose of torque. When we were discussing torque, this point we had discussed. So initially there will be an angle with which the dipole was making with electric field, and then because of the action of torque there will be a certain rotation that will occur. That will be the second angle. So if there are two angles, then use this formula. PE cos theta 2 means the final angle minus cos theta 1. Just look into the notes. I don't remember if Sahal you were there in those classes when we discussed this topic. If you wish, I'll just share this video lecture on the group as well. So what you can see over there, we had seen that cost, like questions do come in the form. If find the work done to rotate a dipole from 180 to anti-parallel position to parallel position like this. So you can put first angle as 180, other angle as 0 degree like this. But if only one angle is given, let's say torque is not rotating it, but potential energy will occur. There is just not a condition that the potential energy will only occur if a torque is acting. So if only one angle is there, it means dipole is not rotating or moving. Then you can simply use PE cos theta, that is P dot E. Now same thing, just apply and analog it for magnetic field. Magnetic dipole is there. If you rotate, two angles are obtained. Use MB cos theta 2 minus cos theta 1. Or you can use minus MB cos theta 1 minus cos theta 2. With minus sign, just reverse it. Best is to use this, avoid negative sign. And if only one angle is given, means it's not rotating. Only a single angle has been made by the magnetic dipole along with the magnetic field. So just use one of the formula for it. That is MB cos theta for that single angle. That is M dot P. Clear, Sahil?
Yes,
Ma'am, will we
And
be
you,
doing this?
Yes.
The
Yes,
questions on this topic?
you did it. Fahad, yes, I think Fahad, you were there when we were doing this. So you had done this. Any doubts from there? Fahad? If you're asking something, Fahad, just then text me or just speak. I think we had the assignment also and we had done the question also from this topic. Remember?
Yes, ma'am. I just forgot.
Okay. So yes, that's why we are doing this in comparison form. Otherwise, this is not included like this in NCERT. In NCERT, you just have the magnetics portion. We are doing it specifically so that at least slight revision of electrostatics will be done. More of the revision part we'll do. Don't worry about it. But please let me know as soon as you'll get your dates for half yearly and all. Just let me know so that we can arrange for the revision classes. And text me done when all of you have written. As you'll keep on writing, just text me done. All right, so most of you have completed. Scroll to the third point. Okay, I'll scroll. So other students who all have completed, you people can leave. I think most probably you'll get an assignment on this. Share your assignments, share your doubts, whatever you have. We'll try to cover the rest portions on Thursday. Okay, take care. Thank you so much.
Okay, thank you, ma'am.